So this is a problem. We want to find M1 so that minus M1 Kx is not a pencil. So in Q funnel case, this is a very difficult problem. Why this is difficult? The point is, so let me do the comparison. For example, if x is if x is of general type, so we have this. We already have Pm not of x. This is non-negative. Okay, and then Collat says that we find a birational model. Say Z. This is a birational equivalent to x. And so that we have a fibration Z to some curve, say C. So this is a fibration. So of course we can assume that this is a pencil. We know that for general type, we can estimate Pm naught. It can be very large. Suppose M naught is large. So, but the point is, you have to find some integer so that this is M1K is not a pencil. So that means if this is already not a pencil, then it's okay. So the difficulty is when this is 0, when this is a pencil, M naught is, then when M, how large can we take integer m so that mk is not a pencil? So this is a very important technique. So Collat says, suppose this is a pencil, then it induces a vibration. So this vibration is induced from m naught kx, right? Suppose this is a pencil, then you want to find a new number which is larger, but in terms of given m naught, so that mk is not a pencil. So this method is the so-called semi-positivity. So the semi-positivity says semi-positivity implies that for any m positive, so f lower star omega z over c here, so m's power, this is semi-positive. Okay, so since this is semi-positive, then you can take some polarization on C, say O1 times F lower star omega Z over C M. So this is generated by globe section. Okay, So this sheaf is generated by low section. The local section of this sheaf is exactly MKF, the section from MKF, where F is a fiber. So take F to be a general fiber. So that MKF has a lot of section. Yeah, this sheaf, say OF, has many sections. As at least two independent sections. Then MK is because this is a local section of this sheaf on C. So because it's generated by global section, so it can be generated. It can be extended to the global section of some sheaf. But this sheaf is like but this sheaf is smaller than so we know that F lower star omega Z over C M tensor O1. This is exactly the subsheaf of F lower star omega Z some number n. Here you can do some explicit calculation. Say n is at least n can be so here we can see we can find some integer m so that n is smaller than n is exactly 11 m naught plus 5. So this is n is smaller than this. When we take n to be some integer like this, 11 m naught plus 5, then that means we can take m to be 5. Then we can see that this is already birational. So this means that 5, 11 m naught plus 5 is birational. So of course this is if you take for any surface, if you take m to be 3 or 2, that's already enough for our purpose. So I don't take say too much on this method because this is we use semi-positivity. The most difficult case is C is P1. But C is P1. Here you should say that you should see that the fiber is at this point is So here you should see that O1 is smaller than F lower star omega Z to m naught. Okay. Once with this, you see this is easy to So this is Kc. If C is P1, the difficult case C is P1. So this is 2m plus. This is 2m. 2m. This is 3m. This is something. Sorry.
If C is P1, then it's omega C is negative.
Yes. If C is P1, we don't need this actually. This is already generated. But when C is not, maybe anyway, it's something. This is a very rough estimation. So you can do very clearly that anyway with this method, you can see that suppose you know PM naught is 2 or larger, then at least we can find some number in terms of this given m naught, so that this is not M1 is not a pencil. So, but this method doesn't work for Q-funnel case. The main point is in Q-funnel case we need this M to be minus. So we need this. We here M is negative. In Q-funnel case, M is negative, and we don't. It's not known whether this is same positive or not. So this is this is what we don't know. And on the other hand, since this method doesn't work, also due to the reason that in funnel case the minus k is not birational invariant, so you cannot use this method. So in reality, what our method is should depend on whether it's Q funnel or weak Q funnel. They are different. So when X is Q funnel, this is relatively, the result is relatively better because we can make use of the property of pickup number 1. In general case, if weak Q funnel case, then what we get is a very, I think a very rough property. I will explain this case by case. So first, so now let me assume that X is Q funnel. Okay, so according to step 2, we already know that we know that minus M not Kx. So this is we can assume that this is a pencil, right? And here M naught is smaller than or equal to 8, not very big. Suppose this is already not a pencil, then it's okay. So we can assume this is a pencil. We want to find some M1, so that M1 is slightly larger than M naught, but minus M1K is not a pencil. So what can we do? So in this case, we should know that pickup number is 1. Okay, pickup number is 1. So we can hope. What we can hope is following. So the result is of course we can assume this is a pencil. So let me assume this with more explicit. So assume P minus M naught. This is this is positive. For some integer. Not. Of course, this is smaller than 8. Okay. It can be 0. It can be 1, 2, or even larger. So the main statement is like following. So we assume that the basket, the Reed's basket, is BI, RI, and I from 1 to S. Okay, so the claim is like this. The claim is like this. So the following is true. Either 1, this P minus M naught is 1, but so the minus M naught Kx is fixed. is a fixed, irreducible, reduced divisor. Either or P minus M naught is 2 and minus M naught Kx. This is has no fixed part, but S is irreducible. S is irreducible. This is moving. Sorry. So this is moving, and S is irreducible. Reduced. Okay, so this is a pencil, of course. This is a pencil. Since this is a Q funnel, so it must be a rational pencil. Must be a rational since Q is 0. Or if this is larger, P minus M naught is larger than 2, then we claim that in this case, so M naught Kx has no fixed part. Fixed part and minus M naught Kx is not a pencil. So there,
property are irreducibility can be reduced and no fixed part. I think from Picard number 1, right?
Yes, but why can't it be be like D1 plus D2 plus D3? Yes, H naught is 1. Pick number 1 it doesn't mean that only means numerically they have a relation, but linearly you can't see, right? So the main claim is like this, but this is conditional, not always true, provided that for any singularities in this basket, we should have one of the following is true. So this is a numerical condition. Let me try to write down. So and which is easy to verify. For example, first, if M is more 0 and plus minus 1 more R, okay, M naught, sorry, M naught. Secondly, M naught is minus 2 more du R, and 3b larger than R, and third, so M naught is equivalent to 2 more R, and 4b. Sorry, I wrote right. So this is B is R over 2 round down. This is 3b. Okay, and then 4 M naught 3 more R, and 4b R, and last case is M naught residue is 4 and more du R and two complicated numeric conditions. But we only need this. In reality, we only need this. We don't care whether M naught is more R is 5. Then R could be very, in general R could be very big. But we don't care others. In our cases, we only care, and even the item 5 is very fewly, very occasionally used. But mostly we use 1 through 4. Okay, so roughly I will explain. What is the idea? The idea is like this. So this is a very interesting idea. So which generalize Alexeyev's original proof in M naught equals to 1 case. Now we are treating the M naught equal arbitrary case. So the idea is like this. Suppose the statement is not true. Then there exists a component. Say E is smaller than E is smaller than this minus M naught kx. So that we have the following relation. Because if you have a fixed part, right? If you have a fixed part, or so if this in the last case, if this has a either this has a fixed part has a fixed part, or this is a pencil. So we can always find some component E. So this is a positive divisor. Not coefficient positive. This is effective, strictly effective, such that we have already this condition. This is minus mkx, okay, minus h naught minus m. So sorry. So here we should write m naught, okay, kx minus e, then plus then minus h naught of e plus h naught of ox is 0. So we can check this. So if E is a component in the fixed part, then this is equal, right? And this is 1, and 1 minus 1 is 0. Okay. In the second case, if this doesn't true, then that means this minus m naught case can be 2, can be s1 plus s2, or because this is a pencil, maybe this is 2s. Then this minus this s is drops by 2. Drops by 1 because this is a pencil. And here also this is this is minus 2. This is minus 1, and this is 1. So so if this is like a 2s, because this is a pencil, then we take E to be s, and then this number is larger than this by 1. Okay, but in this case, this is h naught of if E equals to s, this is minus 2 plus 1, this is minus 1. So it's 1 minus 1, 0. Okay. In the last case, if there is fixed parties, okay. If it's Yeah, if it's a pencil, if it's a pencil, then minus mkx, since this is h naught is at least 2. It's at least 3. So minus m naught kx is 2s. Yeah, so we take e to be s. So similar to the previous case. So we can always have this property. So once you have this property, you know that since it's pick number 1 case, this is pick number 1 case, that means every effective divisor is ample. So you have a higher or higher group, higher homologic group is vanishing, right? So this means that this is chi of m minus kx, sorry, m naught minus chi of minus m naught kx minus e and minus chi of e plus h plus chi of ox is 0, right? So this is exactly due to pick number 1 assumption. Without this assumption, then you cannot get this. But then this is absolutely computable because we have Riemann-Roch. So when we have Riemann-Roch's formula, so we can express this left side into two parts. So one is regular part. Regular part means without taking care of any singularities. The another part is the singular part. So let me write this as delta. Okay, so the regular part is like normal Riemann-Roch without considering singularities. Okay, so delta can be written into 2 parts. So one is the regular part. This is a normal Riemann-Roch part. This is a singular part. So we have this. So let me write down what is the regular part. Regular part, when we put our we write out all the Riemann-Roch formula for these 4 divisors using Meyer's Riemann-Roch. Then we can see that this is a regular part exactly. This is exactly m naught plus 1 over 2 minus kx. And this is minus m kx minus e and e. After calculation. And then we know, because these is strictly effective divisor, so this is ample. This is ample. This is effective. It's also ample. This is ample. So this is strictly positive, right? So the singular part, I mean with singularity, this is like this is like the singular part. The last part doesn't work because here the chi ox without any singularity here. So here singularity appears on the first 3 cases. So let me write out the calculation. So this is there's a Q runs over this basket. So here this is like CQ of minus a constant in terms of the singularity minus K minus CQ minus MKX minus E, and minus CQ of E. Okay, so yeah, after calculation, we found that this is exactly this expression, like sigma j from 0 to s. We have some function f here. Yes. So each, yeah. So I from 1 to s. So j from 0 to L. Yeah. L, what is L? L is the residue module. So sorry, L. So this is Li. So Li is module Ri, because Q is Bi Ri. Okay, so let me write down the result. So this is I Bi plus J Bi. There is some confliction here. What is I? I should be so I is different from sorry, I is local index. Sorry, it should has difference with this. So Li, so it's better I write. So this index, let me denote by sorry, I have to, maybe K. K is local index. Index of E at Q. Okay, so this is K minus F J B I. Okay, so what is F? F is a arithmetic function. So F X. So this is a function. So X bar R minus X bar. This is 2R. Sorry, it's better I don't write I here. I just say this is sum over Q. Then you have in case you have any confusion with okay. So that means Q is BR. Okay. So I don't have to write Li. So this is L. So this is L is M bar module R. Okay, so maybe I can rewrite this. Sorry, this I still conflict with my original. Yeah, let me denote by K. Local index of E. And so here X is integer. Can be some positive integer. Okay. So that's like some calculation in terms of singularities. So you see, this should work for any for any j. Yeah, and K is fixed. suppose you take a singularity Q equals to BR. Then for each singularity you have to calculate this thing. So what can we do? We want to get a contradiction, right? So this is the sum of two terms is 0. And we know that this is positive. We want to derive a contradiction. That means we want to ask for any singularity Q. This sum is non-negative.
So this result relates with this singularity.
Of course, yes. So now, assume this statement is not true. Then we can find a strictly effective divisor E, so that we have this. Therefore, we have this. But
Meng, so maybe just considering the exact sequence from actually say minus m0kx minus e to minus mkx, and then restrict to the e. This just sequence.
No, but this E is not necessarily smooth.
Yeah, I mean, but just you can restrict E.
Yeah.
To minus mkx to restrict to E.
Yes.
But now Picard number 1 implies the h1 of minus m0kx minus E equals 0, right? Actually, you use also there, right? Because it's same as
no. So this divisor E can be very singular.
Yes, but but the h0 and the chi are same, right?
H0
and the chi in the middle part.
H0 of what? This?
H0 of minus m0kx minus E and chi. So why you have?
Yes. This is same, of course. Yeah.
So it means the you have h0 minus mkx is the section of this h0, but they are same because E is the fixed part.
Yes.
But then in the right side we have h0 minus m0kx restrict on the E. But minus m0kx restrict E should has a section, right?
No, how can you know?
Restrict on the E.
Yes, restrict on E.
Kx is positive.
E is a surface, can be very singular.
Yes,
so how can you know? Yeah.
At least the H0 OE has a section, right?
Of course, irreducible. Yeah.
Yes. So minus m0kx is positive.
Yes.
So it should have when you restrict E, then I think it has a section.
This is the point. Yeah, because you restrict. You only know that this is a some way divisor, and not necessary because this is some way divisor only.
Way divisor, but restrict E.
Yes, restrict on E.
Right?
I don't. Maybe.
You restrict ample divisor to ample divisor now.
You restrict ample divisor to. Ample is a numeric condition. It's not very ample.
Yes, but it's
it's ample, but so when you restrict to E, actually E is a part of this divisor. Yeah. So when you take the restriction, I'm not sure whether it has a section. Yeah. Okay.
I think this kind of argument it seems to be always true if you have Picard number 1, if you have a linear system.
Maybe.
Okay.
Anyway, Okay. So the point is we want to assure that for any single singularity, this is non-negative. This is non-negative. So that's why we need this condition. Okay, we put this condition to make sure that all these, when you take this sum, they are non-negative. So that means that this is non-negative, this is positive. So the sum is positive. So, but here is 0. They should be 0. So that's contradiction. Okay. So this is the main method. Yeah. So then, it could happen that this case, this could be 2, and this could be 1. But if we take m naught slightly larger, so first, if this condition, and the following conditions are true, then it's okay. So of course we can treat to make our result very sharp. So we should take care of this case. But we have another theorem to treat this case. So say several times, say 2 times or 3 times, it should be not a tensor. Should not be a tensor. Then roughly we are done. So this is a result. So for this case, so our theorem is like this. So it says the result is like this. So when X is Q funnel threefold, then we can find the integer m1. This is smaller than or equal to 10. So that this is this is not a pencil. So minus m1 kx is not a pencil. So I should say that this is almost sharp. Almost sharp. There is one example where m1 is 8. So where minus 8k is a pencil. Okay, this is this is not really a existing example. It's a theoretical case. We know that in this example, p minus 8 is 2. Naturally, it's not a pencil. But anyway, we can prove that when m1, in this case, we can take m1 is 10 to be 10. Then this is not a pencil. So this is almost optimal. So how about another case when X is weak Q funnel? So what we can do is a very naive lemma, which says that if this is a pencil, then we have what property? So now we study X. This is weak Q funnel. Okay, so weak Q funnel. We have assumed minus mkx is a pencil. Okay, then after birational modification, say we get pi y to x, we resolve the indeterminacy in this linear system. Then we have minus m pi up star minus m kx. So this is something a s plus the fixed part. So this is a effective Q divisor. Okay, so S is so this is since this is a pencil, so this induce a vibration F from Y to P1. Here S is a fiber. S is a fiber, general fiber of F. So what is A? So A is exactly P minus M minus 1. Okay, so then we estimate this. So we have M minus Kx cubed. So this is since this is never and big, so it's like A. Yeah, so P minus M minus 1. So pi upper star minus Kx squared and S. Okay, so now we take R x to be the Cartier index of x, and since x has terminal singularity, singularities. So this implies that the R pi up star minus Kx cubed intersect with S. So this is a positive integer. Okay, so therefore this is larger than equal to P minus M minus 1 and 1 over R x. Okay, so we have this in. Suppose this is a pencil, then there should be this inequality, and then you see that we can get so you have Rxm minus Kx cubed. So this is larger than P minus M minus 1. So suppose this inequality is not true, then it's not a pencil. So so we get the following lemma. So if P minus M is greater than Rxm minus Kx cubed plus 1, then minus mkx is not a pencil. Okay, so this is what we can use. So now so we can estimate the using the Riemann rock to see when this is when this condition is true. Okay, in general it's not easy, but in weak Q final case we know that first we know that Rx is bounded. So this contains a couple of estimation. So the following result is, so for weak Q final threefold, we have Rx. This is smaller than or equal to 8 because this is a bounded family. So theoretically you can get this. And secondly, we can estimate, since Rx is bounded, so we can do some calculation. So the point is we have the formula for P minus M. So this is Riemann rock. We should estimate so that this is always true. So forgive me, I only explain I only provide the result. So the final result is that the result is for this kind of threefold, we can always prove that there exists M1 smaller than 71, so that the condition of lemma of this lemma is true. Therefore, this is minus M1 Kx is not a pencil. I should say that this is a very weak result because this condition, I mean, the lemma, the condition of this lemma is very, too strong. Yeah, too strong. So I should say this is far from optimal. But we don't have any other effective method to do this. Okay, so this is a story for step 3. So finally, step 4. So step 4, as I said, we have m naught. Yeah, we have minus m naught kx. Okay, this is this is a pencil, and minus m1 kx. This is not a pencil. So we have we do it this way. So first, the first step, we take a birational modification. Say pi and y to x to resolve many things. For example, the indeterminacy in this linear system, to make many, make finite number of linear system to be best point free upstairs. So so then we can write the pi up star, the m naught minus kx. This is Q linearly equivalent to say this is a pencil, so it's like something some number a times pencil s plus e1, and m1 pi up star minus kx. This is equivalent to some surface S1. Some surface T. So this is irreducible because this is not a pencil. Plus E2. So E1, E2 are effective Q divisor. Okay. So first, we study a linear system on Y. As I explained in the last lecture, it's enough to study such a inequality, such a divisor. Say ky plus round up, where for m for some suitable m, so this is m plus 1 pi up star minus kx. Okay, so this is larger than this linear system, ky plus round up, so this is m plus 1 minus m naught minus m1. So this is pi up star kx round up plus t plus s. Okay, so by our assumption, s and t are smooth surface, but t is not a pencil, but s is a rational pencil. So here a is something, yeah, A is related to P minus M naught. Anyway, we can replace this by pi up star minus kx, some number, rational number mu naught s plus some E M naught. Okay, so here mu naught is positive rational number, so we only care about this. Okay, so yeah, we want to what we want to do is the following. We use, because this is never big when m is slightly larger, for example larger than m naught plus m1, so this is never big. So the Kawamata-Fivek vanishing says that h1 of this is 0. So you have so you have the so you have this. So h, you have surjective maps. So h naught y ky plus plus this m plus 1 pi minus m naught minus m1 pi up star kx plus t plus s. When you restrict the surface S, so it becomes ks plus m plus 1 minus m naught minus m1. Okay, pi up star pi up star minus kx. Sorry, this is minus kx. Okay, restrict to S plus t restrict to S. This is surjective map. But this group is slightly larger than the following group. This is H naught S Ks. Due to the property of roundup, so we can put roundup outside. So this is m plus 1 minus m naught minus m1 pi up star minus kx restrict to S. Then take some curve C here. So T and S, T is not a pencil, S is a pencil. So T restrict to S is not is a moving divisor. So we can write T S is a curve family which is moving, and by our assumption this can be smooth, base point free. So C is a smooth curve. Okay, so suppose you can first you can verify that this linear system can distinguish different S and different T, different S first, and then we verify it can distinguish different C. Then everything is restricted onto C. Why? Because this is never big divisor. So you use Kawamata-Fivek vanishing again. So you get the following surjective map. H naught S Ks plus. So this is m plus 1 minus pi up star minus kx restrict to S plus C. So you restrict this onto C, a general curve C, then this is Kc plus the roundup restrict to C. Okay, so on a smooth curve C, so you want to prove that this gives a birational map. It's enough to say that this divisor has large enough degree. So then the degree of this divisor, let's say this is dm. divisor dm. Then the degree of dm is at least, since C is definitely big, so you can throw out the fractional part. So it's like m plus 1 minus m naught minus m1 pi up star minus kx and C. So this is on y. Okay, so this is the right hand side is a rational number, but this is so the point is, so you have to estimate this number. But in fact this has a lower bound. We can, so in the final case, this curve family could be either rational curve or elliptic curve or genus greater than or equal to 2. So the rational case, when C is a rational curve, this is very good. This is at least 2. So so when C is a rational curve, let me denote this by this theta. So when C is a rational curve, it's easy to see that theta is at least 2. This is okay. So we have m naught, m1. So you take m to be large enough so that this is, we need this to at least 2. Suppose this rational number is larger than 2, then everything is okay. So this gives a birational map. So the difficult case is GC is 1 and GC is, so for this case we have an effective way to estimate this theta. Okay, this depends on C, whether what is C. So finally, with this method we can do and estimate this theta. So in general, so in fact, in our paper we can estimate this. For example, if GC is 1, we can say that this, so this is if this, in this case we can say that this is 2GC minus 1 over m naught plus m1. Okay, so when this is for this case is slightly better than this. Anyway, we can so this can be initial. So anyway, we can have this. In this case, we have this. But then this is we have to optimize this estimation. To optimize this matching, we have another. Anyway, so I think to explain the method, it's enough to give you this formula. Okay, because this already gives you the lower bound of theta, and then you take m to be larger enough, so that this is at least 2. Then you get birationality on the curve. Then you get birational on the surface, and finally you get birational on the x. So we are done. Okay, so so in this paper we have some calculations, but finally, this is I began to study this problem maybe many years ago, but only until recently we realized that the step 3 is a key point. So we haven't we didn't make any progress on step 3. Now so far I think this paper is still in unsatisfactory for a weak Q final case. For final case, I think the result is very, very good. Yeah. For weak Q final case, the main point is this number is too big. Okay, thank you.